Welcome to the second part of electric fields, and today we'll be looking at something that makes electric fields quite unique opposed to gravity fields. Gravity fields are incredibly simple. They always had the same orientation, being pretty much vertical, onto the surface of the Earth, and always pointed downwards, because gravity was a force that was always attractive in nature. However, electric force can be both attractive and repelling in nature, so you can get to 4 different situations in this case. What are those 4 situations? Well, I've tried sketching them here. Situations A means, in situation A, rather, we have 2 negative source charges in this case. Actually, it's the identical situation. We want to know the field, the electrical field in point P. Now, in both of these cases, it's a negative source charge. And what difference does that make? Well, if it's a negative source charge, E, the sense of E, is towards the source charge. Whereas in situation B, you have positive source charges. And if you want to know what the field E is, the green vector in this case, it is pointed away from the point charge. So this is something you can write down on the first 2 lines here. If QB, your source charge, is positive, the vector E is pointed away from the source charge. If it is a negative source charge, E is pointed towards it. Now, what are the other situations then? Well, the next rule is quite simple. If you introduce a different charge into point P, that charge will have a force exerted onto it. It will, that force that will occur in this case, if you introduce a positive charge in point P, the force will be following along with field vector E. This is the case in both these left situations. You introduce a positive charge in point P, and you will see that your Coulomb force follows along with E. In the situation on the right hand side, you introduce a negative charge in point P. And what is the difference? Well, in this case, the force will be opposite sense of vector E in this case. So it follows the different way. Technically, this is no different from what we have studied when we were studying the Coulomb force. Meaning, if you take a positive and a negative charge, they will be drawn towards each other. These would repel, so it's normal that force, the Coulomb force, is pointed away in this case. Same thing here. These 2 are repelling. Force is pointed outwards. These 2 attract, so force is pointed inwards. However, we just make the single version, the simple rule that if it's a positive charge, it follows your field vector E. If it's a negative one, it goes in the opposite sense. Now, why would we do this? Well, because you can get to slightly more complex situations before we do the exercises here. If you have a single point P here, in this case, right, and it has 2 electric fields active. In this case, E1 and E2. Both are vectors, so you denote that by drawing an arrow above the symbol. Now, what is causing this first field vector? It can be 2 things. It could be a positive charge on this side of it. Remember, if your source is positive, field vector is pointed away from it. Could be, we don't know. But it could also be that you have a negative charge at this side. That will cause the field vector to be pointed towards it. Again, we don't quite know in this situation. It isn't given. Same deal here. We have a much larger field vector E Going from left to right, this can be caused by two things. It could be a much larger source on the right hand charge, and if it's on this side, so if E is pointed towards it, this source charge would be negative. There's also an option that there is a source charge to the left of it, but if it is, it would be positive in this case, because it would mean E is pointed away from it. We don't know. We just get the field vectors E in this situation. Now, if you've got two of those, you can add these vectors together to calculate the total, or to draw at least, the total E force in this case. Now, how do I do this? Well, I first whip out my triangle here, and if you want to add these two vectors together, you start by, and I always use dotted lines to do this, you start by making the projection, the parallel lines of each vector, like this. This is the parallel line to vector 2. If you want to do the same thing for vector 1, right, I draw the parallel line to vector 1, and where do I do this? Not just at any random place. I try to make sure that that parallel line starts at the end of the second vector in this case. Right. If I add these two together, what do I end up with? I'm going to make this one slightly larger, just so it's easier to do. This means that the total field vector that we get in this point P, I'll use a green line in this case to denote that, and I'll use a full line to make it more obvious. There we go. This would be the total size of field vector E in this point. Now again, we don't know what's causing this vector. It could be 4 different situations causing this. All we know is this is the total field vector in this point. And it's quite simple. If I introduce a positive charge, another positive charge in this point P, my force will just follow along with this line, with this vector. If I introduce a negative source in this point P, the exact same force will occur, magnitude-wise. However, it will just go in the opposite sense. That is the meaning of this field vector E in this given point. You don't even have to know what the different source charges are around it. However, it does make sense, because let's consider this positive charge here, and imagine it's a positive charge on this side and a positive charge for this E2. Well, then you would get a slight repulsion driving it upwards from this positive charge, and a slight repulsion driving it to the side, meaning upwards and to the side, it will just follow along these lines. If it was the negative situation, meaning you had a negative charge on this side and a negative charge on this side, the positive charge will be drawn upwards ever so slightly because of this negative charge, and to the side because of this negative charge, meaning you would get this same diagonal type of line. If this charge was negative, it would have been repelled downwards slightly in a diagonal way by this negative charge, and more so to the left too, because of this charge. It would just follow along. So the great thing about being able to draw field vector E is you can just tell what a different charge would do in that certain point. Right? Calculating it would be something different altogether. You would have to use the theorem of triangular calculations and everything. This goes a bit beyond the basic course for now. We'll be doing some simple exercises, or more simple exercises, in the next video. We'll be tackling both this one and this extra exercise, which you will just have to make a note of in your course and try for yourself. I will leave that, however, for the next video.